So we've been adding quite a bit to our toolbox and a fair amount of what we actually have on that initial figure, if you will, of the potential different types of statistical tools that we can use. Now, this is mainly because most of these are the more simple and easy to understand and kind of basic statistical techniques. They were some of the first statistical techniques designed, and they're fairly limited in what they can do in that you are basically comparing two groups either from a known population sample or from two different samples that you took and then divided into two categorical groups. So the final thing we're going to add in this particular lecture is, again, how many variables? Two of them. One of them a categorical, one a continuous or ratio outcome variable. Within that categorical variable, that predictor, that independent variable, we know there's two levels. And then the question, is it between or within subjects? Well, we already handled whether when it is a between subject design or an independent design. We're now going to look at what happens when it's a within subjects design. And that takes us to the t-test for dependent measures, sometimes referred to as the t-test for repeated measures. So again, t-test for independent measures, the top box. Independent measures can also be referred to as a between subjects design. Within subjects design may also be referred to as a dependent measures design. Same, different terms, but it means the same thing. So again, in this case, we have repeated measures. We have an independent variable, an IV, a predictor that's categorical, two levels. However, the same people or, and we'll get into this, a matched sample is what's being used to compare those two groups. Our DV is still continuous, meaning it is either ratio or continuous data. And we have a t-test for repeated measures. So that's our name, the t-test for repeated measures or the t-test for dependent measures. And again, let's put that into our toolbox. So dependent groups. This is to be used within a within participant design or a matched sample. So they're dependent. In other words, we're getting rid of one of those assumptions. The assumption here is not of independent observations because they're very dependent observations. They're the same people. Generally speaking, you are safe to use this design when you have the exact same people being exposed to different levels of an IV. It is a within participant design, it's a repeated measures design, it's a dependent groups design. And what that means, all three of those basically mean the same people are being exposed to multiple condition levels. In other words, you may do a pre-test, no intervention, post-test, and the next day with the exact same people, a pre-test, an intervention, and a post-test. So that would be a within participants design. Now, I do want to note that this is also the appropriate statistic if you made any effort to match the sample. And we've talked briefly about matching, and we will come back to matching as well. But I think what I really want to stress here is that when you match, even if you match poorly, you get to use this design. And that is an advantage. This design is more likely to find significant results. It's a more powerful statistical test. And the reason for that is that the mathematics assume that it's the exact same people are in each of your groups. In other words, the test is designed under the assumption that it is the same people in each group. However, if you make an effort to match different people, you can no longer methodologically use an independent measures t-test. You have to use the dependent measures one, which means basically what that refers to, and what I'm trying to get across is that if you're going to match, you'd better match really well. And if you're trying to get that published or presented at a conference, you really need to spend a lot of time convincing the readers that you really truly did match your sample, justifying you getting to use this technique. So because the groups are equated, either because they're the exact same people or a successfully methodologically sound technique was used to match the sample, the differences between the mean of the first group and the mean of the second group is less likely due to irrelevant differences. In other words, we're no longer having to kind of guess about all of the potential individual differences between our two groups, because there aren't individual differences between our two groups. They're the same people. And because of that, that means that we actually calculate a smaller bottom of the equation, a smaller amount of error variance. So the bottom of the equation when we calculate a dependent groups t-test is always going to be smaller than if we use the exact same numbers and calculated an independent samples test. In other words, the independent samples test is assuming there's individual differences between your groups, and it is a calculation based on that assumption. A dependent groups or repeated measures or a dependent measures t-test assumes there are not individual differences between your participants, and therefore the estimate of variance that goes on the bottom of the equation is less. So again, theoretically, we're looking at the direct difference method. So basically the top of the equation is the sum of the differences between the two groups. And this is basically the same as mean minus mean, and then the variance within each group. Now again, this is pretty much theoretically the same as the equations that we've been looking at other tests, but where we're getting these numbers from is slightly different. So basically what we're calculating is a difference score, D, divided by total variance, the standard variance of D. Now notice that we're not really calculating the individual standard deviations of group 1 versus group 2, and we're actually just calculating the standard deviation of the difference between the two groups, because again, we don't have to assume that the other variance is coming from individual differences. Our degrees of freedom for this test is n minus 1. N is the number of paired observations. So basically, if I've got 10 participants that take the study condition 1 and condition 2, my study is 10 minus 1. 10 people total went through my study minus 1. So we're not calculating how many times they were exposed to conditions, just the total number of paired observations. In other words, how many people were actually in my study. Doesn't matter how many conditions they were exposed to. So when we run the dependent t-test in SPSS, here's the results that we're going to get. So again, we're going to have that top table, and that is going to actually represent the means and standard deviations between my two groups. Now remember, in this condition, these are the same 8 people. So the top line is their C total, the bottom line is their A total, mean difference, standard deviation difference, but it's the same 8 people. Now we're also going to get a line that actually reports the correlation between these two groups. Now we're not actually running a correlation, but we need this information for later, and this information is being used in the calculation of the actual paired sample t-test. So in this case, again, we can take a quick look at this. It just tells us how correlated the two groups are, and we're actually wanting to see some correlation, but remember, we're expecting them, if nothing was happening, they would be highly correlated. In other words, if you scored a 10 the first time, you probably scored a 10 the second time. If you scored a 5 the first time, you probably scored a 5 the second time. That would be extremely high correlation. But in reality, what we're wanting to do, what we're hoping to do, is find a difference. We're expecting that we actually see an improvement or a reduction in scores based on our intervention in these two conditions. So at that point, we'd expect the correlation to actually be lower. We'd expect it to be a smaller correlation. So smaller here is usually better for what we're testing. And again, the main reason we're getting this, I'll get to it, is we actually need that value to calculate our Cohen's d, our effect size, assuming we have a statistical significance. And finally, we're going to get that paired samples t-test, and we're going to basically get, again, that standard. Notice that we've got a mean and a standard deviation and a standard error of the mean. That is the difference score. So the mean difference score, the standard deviation of the difference score, and finally, our actual t statistic, our degrees of freedom, and whether or not it's significant. So walking through it again, we've got our descriptive statistics, we've got our n, though it's the same 8 people, we've got our standard deviations. We've got a correlation that we need later if we have to calculate effect size. And if you want, if you look at it first, if it's a high correlation, you're probably going to be disappointed by the next box. If it's a lower correlation, you're probably going to be happy with the next box. And finally, we're actually going to have, again, those values that were used to calculate the mean difference. Finally, we're going to have our actual calculated t, our actual degrees of freedom, and our actual p-value. Now, if we have significance, in this case we do, p equals 0.048. It's lower than 0.05. Just barely, but it's there. We need to calculate an effect size. Effect size for this one is, again, Cohen's d, but in this case, it's a different equation. We're going to take 1 minus r divided by n squared. So actually, I'm sorry, 1 minus r squared, okay, ignore those last two sentences. We're going to take r and plug r into the equation. 1 minus r is going to be multiplied by 2 divided by n. And again, N is just the total participants, in this case 8. We're going to take the square root of that and multiply it by our T value. So let's walk through where we get those numbers from. Again, we've got the square root of 1 minus R times 2 divided by N multiplied by T. So T is 2.392, R is 0.355, and N is 8. And then we're simply going to solve. And we're going to walk through that equation, and we're going to get our Cohen's d. Now again, remember a Cohen's d of 0.8 or higher is a strong effect, and again we find this is a strong effect size. Cohen's d of 0.96. And again, we're going to report the summary results in the same way we did with the other one. So again, no matter how complex the test, we're still going to walk through the steps. What did we run? And this is also where we talk about violations of assumptions if there were any. We would then put it into English of what was found, was it significant or insignificant, and then we're going to report the statistics. Again, italicized T, the degrees of freedom in parentheses, the actual value, the P, Cohen's d, and then because it was significant and there was an effect size, what did it actually mean? On average, students recalled more concrete words, mean of 13.25, than abstract words, mean of 10.38. And again, we could add a table if we wanted to kind of put a little visual punch to those results. So again, the main points. When interpreting the results of t-tests, the first thing is we have to consider the statistical significance. Is it actually a p of 0.05 or lower? Consider how the groups differ. How are the groups coded and what the means are? So again, remember, we can get negative or positive t-test, and all it means is which group was put in first. And then consider the size of the effect, the absolute difference between the means, that Cohen's d, that effect size. And again, let's talk about when we would or not use and what are the assumptions of these two different tests. So first, on the left-hand side is our t-test for independent groups or between subject design. It's an inferential test for two groups between subject design. There are different people in those groups, and those people have not been matched in any way. We do want to check for systematic differences between the group performances, the DV, so we're looking for simply the difference between the mean of group 1 versus group 2. And our assumptions are that we have a categorical IV with 2 levels, we have interval or ratio DV, we have bell-shaped distributions, in other words, there's no violations of kurtosis or skewness. We have homogeneity of variance, and they're independent observations. The groups were not able to influence each other. The t-test for dependent groups is an inferential test with two groups design, but it's a within subject design, which means the people are either the same people or different people that we have made a methodologically sound attempt to match on important variables. We want to check for systematic differences in individual performance within the groups. So that's one thing I want you just to kind of conceptualize, is that that's one of the reasons we're running that correlation as well. In the independent groups, we're simply looking at the group mean minus the group mean. In the dependent groups, we're looking at each individual's change in performance. How do they perform at group 1 versus group 2? Again, one categorical IV with 2 levels. Once again, an interval or ratio DV. Once again, we have to have a normal distribution of that actual DV. So again, we're looking for skewness or kurtosis. There is still a test for homogeneity of variance, and we're still worried about that. And finally, in this case, we do not have the assumption of independent observations. In fact, by their nature, we assume they're dependent observations. They're very similar people, or they are the same people.